You know how most crystals have this perfectly repeating structure, like tiles on a floor, right?
Exactly. Very predictable.
Well, today we're diving into something different. Quasicrystals, they're ordered, but they don't repeat.
Non-repeating, yeah. Think pentagons trying to tile a floor, you get patterns, but they never quite, line up perfectly everywhere.
It's kind of mind-bending, actually. It even snagged a Nobel Prize, which tells you something.
It really does. And you sent over some, well, frankly, groundbreaking news about their magnetic properties. A real puzzle that seems to be solved.
That's right. For years, the big question was, can these weird structures even have magnetic order?
Yeah.
You know, where the tiny atomic magnets all decide to cooperate.
Like little compass needles lining up. It's been a major focus.
And there are two main ways they can line up, aren't there? You've got ferromagnetism.
Right. Ferromagnetism is the more common one we think of. All the magnetic moments point the same way. North, north, north. They add up.
Like in a fridge magnet.
Pretty much.
Yeah.
And we've actually seen that in some specific quasicrystals, those gold gallium ones with rare earths.
Okay, so ferromagnetism was found.
Mm-hmm.
But the other one, antiferromagnetism, that's been trickier.
Much trickier. In antiferromagnetism, the moments are ordered, yes, but they point in opposite directions. Up, down, canceling each other out on a large scale.
So neighbors are pointing opposite ways.
Exactly. And that kind of order is really, really sensitive to the underlying atomic arrangement, the symmetry of the crystal.
Which is precisely the problem with quasicrystals because their symmetry is so unusual, non-repeating.
Precisely. So finding antiferromagnetism there, that's been the challenge. Could it even, theoretically exist in a stable way?
It's been this huge question mark, hasn't it? For ages, it seemed like most magnetic quasicrystals just ended up in this messy state.
Mm-hmm.
What was it called? Spin glass.
Spin glass-like behavior, yeah, where the magnetic moments are essentially frozen, but in random directions, no long-range order. It looked like maybe that was the default for these materials.
Mm-hmm. A real head-scratcher, like you said. But this new research you shared, it seems to flip the script.
It absolutely does. It looked like we finally have a definitive yes.
Okay, tell us about it. This research comes from a team led by Ryuji Tamura at Tokyo University of Science, right? Working with collaborators.
That's the one. They've published what looks like the first solid experimental proof of antiferromagnetism in a true icosahedral quasicrystal, an IQC.
Wow. Okay, first ever. That's huge. And it's just out.
Just published in Nature Physics, April 11th, 2025. It's really fresh.
And Tamura himself apparently drew a parallel.
He did. He compared it to the very first time antiferromagnetism was found in any material, a regular crystal, way back in 1949.
That really puts it in perspective. So this isn't just an incremental step.
Not at all. It's a landmark finding.
Okay, so what was the magic material? They didn't just use any quasicrystal, did they?
No, they focused on a newer type. It's a gold-indium-europium alloy, ANU, and it's what's known as a psi-type IQC.
Psi-type. And it has that icosahedral symmetry, like a 20-sided die or a soccer ball.
Exactly that kind of symmetry. Those characteristic 5-fold, 3-fold, and 2-fold rotational axes. It's complex.
So the million-dollar question. How did they prove it was antiferromagnetic? What did the experiments show?
They used a two-pronged approach, really. First, they looked at the material's overall magnetic response, the bulk properties.
Okay, what did that involve?
Measuring magnetic susceptibility. And they saw this really sharp dip, a cusp, right at 6.5 Kelvin. Minuscule temperature, obviously.
6.5 Kelvin. Very cold. And that cusp is the signal.
It's a classic signature of an antiferromagnetic transition, yeah. And crucially, they saw it whether they cooled the sample slowly in a magnetic field or with no field applied. That consistency points away from something like spin glass freezing.
Okay, so the material's overall magnetism changed sharply at 6.5 K. Anything else?
Yes, they also measured its specific heat and how much energy it takes to raise its temperature. And guess what?
Let me guess. A peak at 6.5 K.
Bingo. A distinct peak right at the same temperature. That confirms there's a phase transition happening associated with some kind of long-range ordering.
So the bulk measurements strongly suggested antiferromagnetism, but that doesn't directly show the up-down alignment, does it?
Not directly, no. That's where the second technique came in, and it's the really clinching evidence. Neutron diffraction.
Ah, neutrons. Because they can interact with magnetism.
Exactly. Neutrons have their own magnetic moment, so they can essentially see the magnetic moments of the atoms in the material.
So what did they see when they used the neutrons?
Below that transition temperature, down at 3 Kelvin, they saw extra spots appearing in the diffraction pattern. New peaks.
And these weren't just regular structural peaks.
No, these are specifically magnetic Bragg peaks. Their appearance is direct proof that a new ordered magnetic structure has formed, an antiferromagnetic one.
Wow. So they actually visualize the magnetic order.
In a sense, yes. The positions and intensities of those peaks tell you about the magnetic structure. And crucially, when they track these peaks as they warm the sample up, they vanished right around.
6.5 Kelvin.
Precisely. They popped up abruptly as it cooled below 6.5 K. It all fits together perfectly. The paper even has graphics showing this.
That sounds pretty definitive. Direct evidence. Okay, so why this material? Why does this gold-indium-europium quasicrystal succeed where others showed that messy spin glass stuff?
That's the really interesting part scientifically. It seems to come down to a property called the Curie-Weiss temperature. It's a value you can extract from magnetic measurements that tells you something about the underlying magnetic interactions.
Okay.
Now, most of the previously studied magnetic IQCs, the ones that ended up as spin glasses, they had a negative Curie-Weiss temperature.
Negative, meaning what?
Well, loosely, a negative value often hints at competing interactions, frustration, things that favor disordered states like spin glasses.
Well, but this new on and U one?
It has a positive Curie-Weiss temperature.
Oh, so positive good, negative bad for antiferromagnetism here.
It appears that way in this context, yes. The researchers argue that this positive value is key. It suggests the dominant interactions actually favor this kind of antiferromagnetic alignment in this specific quasiperiodic structure.
That's a fascinating distinction, a fundamental difference in the magnetic forces at play.
It seems so. And they found something else just as critical.
Oh, yeah? What's that?
How incredibly sensitive this antiferromagnetic state is. They tweaked the composition slightly, just changing the electron per atom ratio a tiny bit by substituting some elements.
Just a small chemical change?
A very small change.
Yeah?
And boom! The antiferromagnetism completely disappeared.
No way. What happened instead?
It reverted right back to that familiar spin glass behavior seen in the other IQCs.
Wow. So it's living on a knife edge, magnetically speaking. That electron balance is crucial.
Absolutely critical. The big takeaway seems to be positive Curie-Weiss temperature plus the right electron concentration equals antiferromagnetism in this IQC. Change that electron count even slightly, and you lose it.
So this isn't just finding one example, it's potentially uncovering the recipe.
Exactly. It gives scientists a handle, parameter, the electron per atom ratio, that they might be able to use to design other antiferromagnetic quasicrystals. That's a huge step.
It really feels like this settles that old debate then. Can antiferromagnetism exist in a real quasi-crystal? Answer, yes.
Definitely. Professor Tamara was quite clear about that. He said this resolves that long-standing issue, and he's clearly excited about what comes next.
What kind of potential did he mention?
He talked about unprecedented functions, things like materials with ultra-soft magnetic responses.
Ultra-soft magnetic responses. What does that mean practically?
Imagine materials whose magnetic state can be changed very, very easily with minimal energy input. That could be revolutionary for things like, well, spintronics, using electron spin for faster, more efficient computing.
Ah, using spin instead of just charge.
Right. And also magnetic refrigeration,
Yeah.
using magnetic cycles for cooling instead of compressing gases. Potentially much more energy efficient and greener.
So efficient electronics, greener cooling, those sound like pretty significant potential applications.
They really are. And it connects to bigger goals, too. This kind of fundamental science could eventually contribute to things like the UN's Sustainable Development Goals.
How so?
Well, SDG 7 is about affordable and clean energy, and SDG 9 is about industry, innovation, and infrastructure. More efficient electronics and cooling technologies fit right in there.
That's a great point. It's not just a cool physics problem. It has potential real-world relevance down the line.
Definitely. It basically opens up a whole new research field, the study of quasiperiodic antiferromagnets. We just didn't know they existed for sure until now.
Incredible. And of course, work like this involves a dedicated team. You mentioned Tamura.
Yes, Ryuji Tamura, Takaki Abe, Takuje Sato, Max Avdiv, key people involved. And it relies on significant support, too.
Funding from places like DOT.
Japan Society for the Promotion of Science, Japan Science and Technology Agency, Australian Nuclear Science and Technology Organization, Japan Atomic Energy Agency, Institute of Solid-State Physics. Major collaborations and funding are needed for this level of research.
Absolutely. It's a massive effort.
And again, the full details are in that Nature Physics paper for anyone who wants the nitty-gritty.
Right. So, for everyone listening, the big takeaway here is pretty clear. Antiferromagnetism, that elusive magnetic order, has finally been nailed down in a quasicrystal. It's a first.
A huge first.
And it's not just ticking a box scientifically, it unlocks this whole new area of material science with potentially game-changing applications on the horizon.
Absolutely. And it really makes you think, doesn't it? If just tweaking that electron ratio slightly can flip the magnetic state so dramatically.
Yeah, from ordered antiferromagnetism to disordered spin glass.
Right. What other unexpected properties are lurking in these quasiperiodic systems? If we can control magnetism this finely, what else might we be able to tune?
What completely new technologies might pop up that we can't even imagine right now, just based on understanding these fundamentally different materials better?
Exactly. It's the kind of discovery that opens more questions than it answers in the best possible way. Lots to explore now.